Welcome back, physics, to part 2 of the work, energy, and power notes. In this part, we're going to be discussing what energy is. So far, we've been investigating how one does any work on an object, and we learned that work is completed when force is applied over some displacement. And those two things need to be parallel. They need to be in the same direction. This is important. If the force and the displacement are not in parallel, if they're perpendicular, fully perpendicular, then no work has been completed. That displacement was not caused by that force, and therefore that force did not do any work. So when we do work on something, what we have done is we have transferred energy. And so we can write that out as a delta E. So one way we can think about this is that when we work on something, we've transferred that energy into that object. So let's say I work on some homework, right? If I've worked on some homework, the energy was inside of me from probably when I ate some food earlier in the day, and now I've transferred it into the piece of paper that I was working on, into the Google Doc that I was writing my assignment, what have you. The energy is now stored there. It's no longer in myself. It's now in this new thing. If I clean up the house, right, I've organized some things. If I clean the dishes, right, the dishes now have that energy stored in them in some way. Notice that you cannot see energy. There might be energy in a battery, but I just see the battery. I don't see the energy inside of it. Same thing with work. So something that I neglected to talk about before, and you can fill this in at the top of your page, is that the units for both energy and work are units of joules, or capital J. We are now away from Newton for a little bit. Energy is not something that Newton really discusses. There's a guy named Joule, and he named it after himself, just like Newton named the unit for forces after himself. If you're looking for something to be named after you, finding a unit is a pretty good way to do it. I'm looking for a Zwicky in the future. How many Zwickis is that? That's what I want people to be asking. Now, energy can take many forms, but for us, we're only going to be considering two kinds: gravitational potential energy, gravitational potential energy, and kinetic energy. So gravitational potential energy is going to be energy that's stored based on the forces due to gravity, and kinetic energy is going to be your energy of motion, right? We talked about kinematics at the beginning of our school year. So when we use kin, K-I-N, we're talking about motion. So I think the best way to look at this is to start with our gravitational potential energy. So let's consider a box being raised. Okay, so we have a box, and it's going to go up to here. Okay, so if we're considering gravitational potential energy, let's say that the box on the ground has no potential energy. The potential energy here is 0 joules. Okay, we're just going to set this as 0. Now, once it's lifted up, it's going to have been moved against gravity and has the potential to fall. So its value is going to be something. And specifically, it's going to be the force of gravity times the height it was raised. Now I'm going to use h instead of just a regular distance d because we want the force and the displacement to be in the same direction. And I don't know, if I move vertically upwards, I have been raised up a height. So if this is the case, I can actually write it out in a different way. I can write it as mgh, right? The mass of the object, the acceleration of gravity, and the height it was raised. And so this is the equation for potential energy. So now what I would like you to do is to finish out these notes on your own. Try out your understanding and see if you can answer the couple of questions at the end. All right. Now that you have answered those questions, we are going to fill in the last equation. So you've been given 2 equations so far. I'm going to give you the last one. It's kind of quick. Sometimes we've used the word power, and power is related to energy and work. Power is going to be represented by a capital P, and it's going to be the amount of work completed over a certain amount of time. The units for power are important to know. You might have heard about wattage before. So the unit is called a watt, or a capital W. So when we were thinking about our people writing the one-page paper, this is where we can start to think about the time. So the people that wrote the one-page paper in one night, right? Well, they do the one page in, let's say it was 1 hour, right? So we would say this is, right, like 1 page watts or something like this. One page watts. But the people that do it in 4 nights, right? Well, they do 1 page in 4 hours. And so they're only exerting 0.25 page watts or whatever, right? So because they took a longer period of time, they don't have to exert as much power, right? If this is a light bulb, it's not going to be as bright, because you are exerting the same amount of energy, you are changing the amount of energy, but over a longer period of time. So you could collect the same amount if you, and let's say there was like a solar panel or something, right? At the end, the solar panel would have charged the battery to the same amount, but it would take longer for that solar panel to pick up as much energy per hour. And that is what power is.